Today we're going to talk about definite integrals. Before we define what a definite integral is, let's do some thinking about a related concept. So let's start with an example that might feel really easy. So our question is, how far does a car travel if it's driving 30 miles per hour for half an hour? Probably intuitively you know that that's 15 miles. How do we know that? Well, we want to know miles. So if we do 30 miles per hour, and we multiply that by the number of hours that we've driven, so in this case it's half, this will give us 15 miles. Now we can think about this in terms of a graph as well. So we can graph our miles per hour on the x-axis and our time on the y-axis. So we go 30 miles per hour, and we're doing this for half an hour. These units are obviously not to the same scale. All right, so then 30 times 1/2, which is what we're interested in, is the same as the area of this rectangle here. So this brings us to the concept of area under a curve. In particular, we're interested in signed area under a curve. So what does this mean? This means that if we draw out our function f, the area under the curve in between an interval is going to be exactly what it sounds like. Now, in particular, we're looking at the signed area. What this means is anything below the x-axis, we're going to subtract. So let's take a look at an example. So let's say we have a graph that looks like this, and maybe let's give ourselves some units. Maybe this is a 2, this is a, I don't know, -1, maybe a 1, 2, 3. So we want to know what the signed area under this curve is. So we'll start with the area that's above the x-axis. So that's here and here. So we can calculate these areas by knowing the area of a triangle, which is 1/2 base times height. So in this case, we'll have, for our first triangle, 1/2 base times height. And then we also have a second triangle over here, which happens to be the same area. So we've got a base of 1 and a height of 2. All right. But then we also have this piece underneath of the x-axis. And here we're going to take that part, and that we're going to subtract. So that's 1/2. Our base again is 1, and now our height is also 1. So taking that all together, this will give us our signed area, which in this case would be, let's see, we've got 1 and 1 gives us 2 minus 1/2. So our signed area here is 3/2. All right, this is slightly different from what we might think of, which would be adding together all of these areas. Here, we just want to make sure we subtract what's underneath of the curve. All right, so this is the signed area. Let's take a look at a slightly more complicated example. So let's say we have our car again, but now it's not traveling at a constant speed. Let's say it's traveling at 60 t miles per hour. In this case, t is going to still be measured in hours. So our question is, how far does the car travel? Well, here, let's think about what we've been talking about, which is relationship between distance and speed. So we had said a couple weeks ago that the speed of our car would be the derivative of the distance, right? So now we don't have the distance, we have the speed, and we want the distance. And what undoes derivatives? Integrals, that's what we talked about last time. So we know that our distance will be the integral of 60t dt. And if we want to take that integral, what we're doing there is we're saying, okay, what function, when I take the derivative of it, will give me 60t? So that is 30t squared. And you can double check yourself on this one. If you take the derivative of this by the power rule, we'll pop that 2 out front. That'll give us a 60, and we'll be left with t. And then technically we also have this constant, but we can let's call this constant 0, because in our problem, we're going to be starting at time equals 0. We'll be starting from rest. Okay. So our distance is t squared. So let's see what happens after half an hour. So our distance in half an hour is 30 times 1/2 squared, which will give us 30 over 4, which you can reduce to 15/2. Okay. So let's try and think of this as a graph like we did with our last example. So here we've got our miles per hour is 60 t. So after half an hour, we're at a height of 30. So let's take a look at this area. Under the curve, again, our area of a triangle is 1/2 base times height, which is 30 over 4. Now, this is not a coincidence. This always happens. So if we're looking, there is a relationship between integrals and area under the curve. This should not be super surprising. If we think about taking the derivative of something, we're effectively dropping a dimension. So if you imagine graphing your derivative and you want to know what would give you that derivative, or trying to up the dimension by multiplying by x down here, roughly. All right, so let's talk about a definite integral. A definite integral on an interval is just the signed area on that interval. We're going to denote it like the indefinite integral that we had. So we've got f of x dx. If you think about this, this f of x is the height of our function, and we can think of dx as the width. This ties into Riemann sums, which we're not going to talk about right now, but basically what you're doing is you're finding the area of little rectangles here. Our a and b on either side of this, these are called our bounds. Okay, so if we want to evaluate a definite integral, that's the same thing as asking what's the area under the curve. All right, so let's do this example. We want to know what is this integral. This looks really complicated, but if we think of it as area under a curve, what is this square root of 1 minus x squared? So that equals y. This is just a half circle. So this is a half circle from -1 to 1. And what that integral is asking for is the area underneath of this curve. So this is half the area of a circle, and the area of the circle is pi r squared. In this case, r is 1, so we've got pi 1 squared. So this area is just pi over 2. All right, so these are definite integrals. Definite integrals is just asking for the area under the curve on a certain interval. Now we've got a couple of properties that we can talk about, and these are fairly intuitive. So let's take a look at this first property. What it says is if we're looking at the definite integral from a to a, that should be 0. This is not that surprising because if you imagine the area under the curve at one point, the point A, there's no area there. So that should be 0. This next one is saying I can think of my function. So let's say here's my function, A, B, C. I can think of this area under the curve either as an entire piece from A to C, or as 2 pieces, one from A to B and one from B to C. So even if I divide it in half, if I add up the areas of those halves, that'll give me the area of the whole. So this is not that surprising. This third property is so that the first 2 will still work, basically. So if we think about this as, let's say we've got the integral from a to b of f of x dx, and let's add on to that the integral from b to a of f of x dx, then our second property says that this should be the same thing as the integral from a to a, because those are our 2 outer endpoints. But the first property says that the integral from a to a should be 0 because there's no area underneath of a single point. So in order for that to be 0, these must be opposite of each other. So you could think of subtracting this integral from a to b from both sides. So that's how we get this third property. And the last two properties are very similar to the ones we talked about with indefinite integrals, where if you're taking the integral of a sum of functions, you can take each of those integrals separately and add them together. And if you have a constant, you can pull the constant outside of the integral. So to recap, definite integrals are looking at the integral of a function on a specific interval from a to b. Those are bounds of integration. And if we want to look at a definite integral, what we're really asking about is the area underneath the curve, and specifically the signed area underneath of a curve.